let's just start here and focus for a second. Can everybody look up here and tell me which is the most precise measurement? This is mass on top, and then 3 different volumes, 3 different lengths. Which one's the most precise?
Mass is the most precise.
Everybody agree? Mass? Yeah. Like they're not, like these are in the tenths and the hundredths. These are way out there. Right? And that's all fine and dandy, but that's not going to run the show. When I get density calculated, I should only reflect the precision of the least precise tool. Got it? So how do you do that? So we've developed a method, and it's called tracking significant figures. That can be misleading sometimes, but basically what we're going to do is track uncertainty through a measurement, through a calculation. You with me? Okay, so there's just a set of rules, pretty simple, okay? And they all are based on what we call orders of operation in math. So I'm going to just remind you of that. And we can skip parentheses for this because it's not relevant. So if we go roots and powers, right, stuff looks like this. And just so you kind of remember, right, so this is the same. Whoop, this means the same thing. When you start to raise it to the negative, that's like rooting it. So you got roots and powers, you got multiplication and division. Right? So that is like x times y divided by y, whatever. And then you got addition, subtraction. This is kind of the order. This is the first priority, that's second, that's third. That would be the order you would do things in. Now, that's what I can do calculation-wise. So in here, it looks like I've got division and I've got multiplication. Correct? All right. So there's just simple rules that will allow that the proper amount of uncertainty in a popping out in the answer. And once we learn that technique, it's pretty simple. But you kind of have to learn that. So it's when it's roots and powers, multiplication and division, then what we say is you've got to count significant figures. And the significant figures are non-zero figures. So in this case, it's pretty straightforward because, you know, there's a lot of significant figures here. These are basically 3. This one is 3, but we'll talk about that. The zeros are the ones that get you, so we'll have to kind of remember how to do that. But these are all 3 along the bottom. So there's only 3 significant figures as the least precise. So my answer can only show 3 significant figures. That's the way you do it. So when I get done, I calculate this big old number, see it? But I say of that, I can only report 3 non-zero numbers. So I basically should be reporting 1, 2, 3. So it's 230, is that 0.230 would be the right amount of precision. Okay, now what I do with that is I usually take this digit and I round off this next one. If it's 5 and up, then I round this up. If it's 4 and down, I round this, leave it the same. So in this case, I really say 0.231. And that's that piece. Now that's just how I would do this one, but I'm going to give you the exact rules so you know how to do any one. And then we'll practice, and then we're going to be good with that. Sound good? Now the nice thing about units, we started working with units, right? Like I started to show you how to put things over other things, and things cancel and things multiply, right? So it's kind of nice once you learn how to do that, you can just start to learn how to do fancy units, these what are called derived units, where these are fundamental units where I didn't try and derive anything, I just wrote them as is. If it's on top, I multiply it, well there's just a gram on top, and the centimeters are times each other, so that's centimeter times a centimeter times a centimeter, that's centimeters cubed. They're on the bottom, so I really would write the unit as is. Grams divided by cubic centimeters. That's the right unit, just as it came up here. Follow what I'm saying? Let me expand on that thought, just a little bit, so just to make sure. So if I did 4 grams, and on the bottom I did 2 centimeters times 2 centimeters, don't worry about the answer. Well, you could do that, 4 divided by 4, it's 1, okay, good. But now when I go to do the units on this one, what do I see on top? Grams, and what do I see on the bottom?
Centimeters squared.
Centimeters squared, and you just write it as is. That's what I'm trying to say. Right? The units are right there in front of you. Just rewrite them according to how they got all mushed together. If anything cancels, it cancels, which is glorious. Right? So that's that. So now let's kind of learn how to keep uncertainty. All right? How to keep uncertainty. And by the way, I was just trying to show you that according to the calculation, water is more dense than that cow, so that cow would literally float, which is quite a thought. All right, here we go. Here's the rules. So I'll give you a minute with this, because these you need to know. And while you do that, I'll time my sheet, so I don't trip. This whole business is about over here. It's very excited. Something to do with projector. Guys got this down, and then we'll kind of talk it out, because there's some more you kind of need to know around it. First off, just let's see. First off, what are significant figures? So we'll just start with that to begin with. So I'm going to show you kind of the rules for all that. So this is going to be all non-zero digits are significant, so that's easy. So if I got a 5, 4, 6, there's no zeros in there. There's definitely 3 significant figures. All trapped zeros are significant. So 405, that has 3 significant figures. Okay? Trailing zeros are significant. Now now you know why. Because I meant to put that because the tool is better than one that measures to here. Right? Remember, this is something that actually measures to 1, so I put a digit out there to show it is good. I see a line for every 1 on this. Right? And if I put 2 zeros, that means it's good to the tenths, like, right? It came from the tool, so that makes sense. Leading zeros are not significant. That's the one that throws people off. And I get it. It kind of is like, well, isn't that important? There's a way to do that if you want to kind of see why that, I mean, if you want to just play with it a little bit. Let's try it, see how close I could get. I think I could do this. Let's just do this. we're going to use a number that's way too precise, like this. And then we're going to use another number that's way too precise, like this. So let's say you took 0.045 and multiplied it by 3. Tell me what you get as an answer. 0.045 times the number 3. Anybody let me know. 1 point what?
No, point, 0.135.
135.
135.
No,
Yes.
Yes?
Yes.
Okay. Now, if I did this, what would I end up with?
Point 1.18.
And what's after that? Nothing?
Nothing.
Where's it varying? In that digit, huh? So what I'm saying is, remember that if I'm doing a fluctuation, wait, I did that wrong. Let me do this again. Sorry. Sorry. Try this. That makes no sense. It kind of does, but let's do this. If I did this 0.045, that means the uncertainty is in the 5. Now let's do this calculation, 0.048, because that's kind of the same number, right? And then do times 3. That might work out better. We'll see. I'm just doing this on the fly. What do you get as an answer here?
0.144.
Now do you see where it's varying? So in the calculation, right, the variance should be representative, which it is, the second digit, the second significant figure. Because remember, that number could have very well been that number. There's no difference. And then what does that do to the outcome once you do a calculation? If I was saying, oh, I've got 3 significant figures, well, that would mean all these are significant, but they're not, because I'm really not changing this, I'm changing this. It's really 2 significant figures. And you can do that exercise over and over, and that's where the rule got derived from, is people just said, what happens when you walk it through a calculation with multiplication division? And they go, well, if you use this, count the significant figures, and then write that many significant figures in the answer, you'll take care of all this without having to do this exercise. It magically does it for you. So, you count significant figures for roots, powers, multiplication, division. That's how you do that.
So hypothetically, if, like, because it's 135 and 144, say it was 135 and like 137.
Then I would start to go, oh wait, maybe it was 3 significant figures.
Okay.
But that's not what will happen. You'll start to see that it starts to play with the
And
second
you just look
digit.
at the uncertainty to where that next number differs between the two.
Yeah.
Okay.
But you bypass all that. But see, I'm trying to help you guys realize, because you know, this you're college, right? In high school or whatever, they just said, here's the rule, you did it, you never knew why. I'm just trying to elaborate, like, here's where this thing came from. It was based on real facts, like the tool to begin with has uncertainty. Now I do a calculation with the tool, that uncertainty has to carry through and be fair to the answer, and that's where the rules come from. Now the last thing is zeros at the end, they're no man's land. Like, I'd have to leave it there, because if I get rid of it, it's not the same number, right? If this is money, and it went from 405 to 4,050, you're like, that's a big difference, right? So, the number, but do I mean to leave it there, or is it just a placekeeper? So guess what? We have something that takes care of that, called scientific notation. So, I meant to leave that number there because this is where it varies. In other words, my tool measures to the tens. It literally has marks for 50, 60, 70, 80. So I wrote one more digit to show that it's that good. But I need that. So what I do is go 4.050 times 10 to the 3, and boom, I've got 4 significant figures. But if I wanted to show 3, and if I want to show 2, And if I want to show 1, yay scientific notation. Got it? So, officially, if I write something in a journal like this, it'll get flagged. I don't know how good your tool is because of how you wrote that number. If I write it like this, it's like, cool.
4050 is 4 significant figures, right?
So,
Or is it
this
just
is
3?
4 because all the zeros are after the digit. So this is 4 significant figures.
Mm-hmm.
This is 3, this is 2, and this is 1. It's the same number,
Mm-hmm.
just with more precision. Is that good? Yes.
Yeah, kind of. So like, 4050 by itself, just like, let's say that we have it just like this, though it's wrong. It has 3 significant figures.
No. No is what I'm trying to
Unless you
say.
add a 0.
No, I'm trying to say no. Like, we don't do that. We don't hang a 0 out here.
Mhm.
It's not okay in science. That's what I'm trying to say. To communicate this properly, you have to do it like scientific notation, because this is unknown. It's no man's land. It's not. It doesn't use any rules because I don't have rules for it. You see people, excuse the language, they bastardize this sometimes. They do stuff like this. They're trying to say that that's a significant figure.
Mhm.
Most of us know what that means, but it's not technically correct. Like people say, no, we're not going to go into that, like create our own new form. Like, just stick with the rules. You know how to use scientific notation, use it. Is that okay? You guys all right with that? You feel like we're being really nerdy and nitpicky right now? It's okay. Yeah, but it's good.
So you prefer like the one on top then? Like the first one you wrote?
This?
Yeah.
Oh, well, no, it depends what your tool was.
Oh, okay.
This is a very good tool. This is a really crappy tool. Right? In fact, this tool is, it means nothing because it's uncertain in the measurement area. So the very best tool I have that you could maybe measure 4,000 with, better have marks at 1,000, 2,000, 3,000, 4,000, and if so, I'd write it like this. And I would have written it like, if I marked right on the 4, I would have written like that, you see? And then this is a better tool, and this is a better measuring tool.
Okay.
Yeah, it's good. Those are good questions to ask, so you get it clear. All right, so there's that. Everybody get your rules for sig figs? Good? All right. Now, well, I left out addition and subtraction. I do have to do addition and subtraction sometimes, right? What do I do with that? So I'm going to back up to the rule just to remind you, when performing addition and subtraction, keep the answer as precise as the least precise number that is being added or subtracted. I better see an example. What the heck do you mean by that, right? Anyway, yeah, okay, we talked, I just said what I made, right? This is just a repetition of that. By the way, there are numbers that are in formulas that have no uncertainty at all. Like, it's part of the formula. Like 1/2 mb squared is part of the formula. The 1 and the 2 have no significance there. Follow? Metric conversions are very significant, or insignificant, because they are truly infinitely, they're made that way. Again, that's why we love the metric system. Because there are 10.000 centimeters in a millimeter, or whatever, or millimeters in a centimeter. Just, this is locked. There's no significant. But when I do the imperial English system to the metric, I gotta go get digits again. So there are 2.54 centimeters in an inch. That's 3 significant figures. And if I need 4, I gotta go find a digit, and I have no idea what it is. I mean, I just don't know it. Pain, right? Okay. Constants, the periodic table has significance in it. So, you guys pull out your periodic table. So can I keep going with you? You can look and I'm gonna look with you. I'm gonna go to the element, up top left is hygiene. See it? See the bottom measurement of the weight of hydrogen? We'll learn more about this as we go along, 1.008. That actually is 4 significant figures in the measurement. Do you see it? If you go over to boron, number 5, that one has a little bit more precision. It actually has 5 significant figures. So as you use them off the table, they literally are, some are very precise, some are not. Some are really, I was trying to pick one out that's just kind of has very little precision, which means it's really uncertainty. It's uncertain in its stability, but that's a side note. But you can poke around and find that when you have them there. I don't know one right off the top of my head. Okay, so there's that. Got that, got that. Okay, let's talk about this. This is where I was trying to get to. Addition and subtraction. Here's what I mean. If I took 345.0 and I added 22, I get 367. Good? Now let's go back and analyze uncertainty. This is precise to what place? 10th. Everybody agree? This is precise to the ones, right? So my answer can only be precise to the ones. And I will write it that way. Even if it came out with a weird fraction, I'd write it to the ones. That's what they mean by keep the least precise. So that's pretty simple. Now like this. Here's a good example. I subtract that, I get this. Again, to the tenths, to the hundredths, my answer has to show tenths, even though I don't need it. It comes out as 0. I still write it to show that this tool was that good. And it was the worst tool of the two. So my answer is still that good. That's pretty simple, right? So everything else counts significant figures, addition, subtraction, keep the least precise. That's your rules. Pretty simple. What rule am I going to here? Least precise or significant figures?
One has 4 and one has only 1.
Significant figures.
Significant figures is the way I'm doing it. And then to do sig figures, you said this has
4.
and this one has
1.
1. So the
Should
answer
be
should
1.
only have
1.
1. So I gotta do scientific notation. I have no other options. Cool? Well, I take that back. This is truly, oh, no it isn't. It has 2. So yeah, that is correct. I have to do scientific notation. Okay, now I'm mixing and matching. I'm doing addition and I'm doing multiplication. This is the hardest. This is what you got to do. You got to break it apart. The first thing I do is this. You guys pull your calculator and tell me what that answer is. And then you'll see what I'm writing up there.
628.88.
628.
0.88.
You guys agree? People getting thumbs up around the room? Good. All right. Now we're going to break it apart and say it's multiplication, so count sig figs. How many you count?
2.
2. So to be fair, I can only write 2, so I would write this as
630.0.
yeah, and that would literally, and then I just make a note to myself. That's where I'm using this in the calculation. I'm just basically saying, oh, that's only 2 significant figures, or to the tenths. But now I take that number and I add it, because that's the next thing I do. And what would that be on your calculator? 630 plus 23.4.
664. Oh. No, 660.
6.
6.
We're going to add these as is. Just add them right up. Just 5.
3.4.
Yeah. And now I just go back and go, okay, but I got to keep least precise. This is good to the tenths. That's glorious. This is only good to the
1.
the tens. So it's like, oh my gosh, I can only write an answer to the tens. So really, this is the proper answer, 650. So I have to then go up. I can't do that. I can't do 650. I got to go 6.5 times 10 to the 2.
So you always
Now
just wanna-
remember, again, because I know a lot of times you're looking at this going, oh my gosh, do I have to do all that? Yes, when you mix multiplication and addition. It's very uncommon in science, by the way. Like most, all the stuff I do is either a quick addition change, like I'm changing temperature, like Celsius to Kelvin, I'm adding. About everything else you do tends to be multiplication, so in that case you just count sig figs and get to the end and you got an answer. It's very simple. But when you get in those weird things where I have a formula that has a, you know, mx plus b, a y equals mx plus b type function, it would have addition and multiplication, then I have to buckle down and go, all right, count sig figs first, get the answer, keep least precise and add, and this is just an exercise for you guys at this point.
Why did we end up using 2 sig figs?
Okay, let's start at the beginning. It's very important. How many significant figures in this thing? 2. So that's kind of running the show, isn't it? So that started the whole thing because that's the first calculation, which gave me 630. And that only has 2. Now when I go to add, I don't count sig figs anymore. I'm looking for least precise, which still puts it in the tens place. Or tens place, sorry, not tens, tens.
So if you have like the number 100, that's like one significant figure.
Well, if you have the number 1 times 10 to the 2, yes, that's one significant
So you
figure.
always write it as significant figure.
You always write it scientific notation if it's a number with
Right.
trailing zeros.
Okay.
Unless you get to the right side of the decimal, then it's like, okay, now we're doing it again, we're fine.
Oh, but 653.4 doesn't have zeros. Why can't we write down 650?
So say again?
653.4, it doesn't have trailing zeros.
Oh, so
We
you
still
are,
use a scientific notation.
yeah, so if you were sitting here, I have to still write scientific notation because the place where the precision's sitting is there, not there.
Mhm.
So I have to go back out here to make sure I'm keeping 2 sig figures. Because if I did this, it's uncertain what that means. No one knows how to interpret that.
Mhm.
Did you put the 0 to hold the spot or not? Okay, again, I just want to reassure you guys, you know, because I think about when I'm sitting in your seat looking at this lecture and I'm going, are you gonna write a test with like 5 of these, like addition, multiplication added together? It's like, no, I'll ask one of those. The bulk of them is, can you count sig figs? Do you know to do sig figs when you do multiplication, division? Do you know how to do addition, subtraction with least precise? That's what I'm most concerned about. But I'll throw in 1 or 2 of these though so that you know how to do the big skill. And it is as much a pain in the butt for me as it is for you too, by the way. Like if I'm doing writing up a journal something and I realize like, oh crap, I gotta drop off and get my sig figs and then I gotta go least precise. And it's like, yeah, here we go. There's no magic to it. It just does not go easy. If that's of any consolation. Is that consoling? I don't know. Is it? What's the vote?
Mildly?
When I'm in pain, is it nice to know that somebody else has the same pain? I don't know. You know?
Depends.
I always feel better when it's like none of us have pain. Then you're like, now I'm feeling good about it. All right. So here's your practice. You guys work on these on your own for a little bit. You'll see how you have a little chance to do it. So, you know, now I'm going to try, on this last one, I'm basically saying, hey, here's the purple rectangle, by the way. Measure the length, so you'll have sig figs by if you know how to measure it properly. Then if the width is this, then calculate the area and keep the right sig figs. That's what I'm basically asking you to do. And of course, when you advance the slides, which would be nice if you're practicing. This is what I've got.
Nice.
Pretty good. All right, that's the end of that.